Okay, so let's get her started. I kind of feel bad last week for ending so early. So what I'm going to do from now on is I brought the textbook, and with any extra time I have at the end, I'll let everyone who wants to go, but whoever wants to stay, we can just choose random questions from the book, and I'll try to solve them, if that's okay. Okay, so this week we're going to do double and iterated integrals. Do you guys remember Riemann Sums from last year? Do you remember okay, so we're going to quickly go through Riemann Sums, and I'm going to show you how to extend Riemann Sums to one extra dimension. The Riemann Sum definition isn't altogether too important. It is important for those of you who are going to do engineering, if you actually want to do things like numerically approximate integrals and things like that. So it's not absolutely essential that you understand it. So I'm going to go over it very, very quickly. Okay, but before I start today, here are some requests or pleas that I have with you. In order to do well at mathematics, you're going to have to practice as much as possible. Right, so try to find yourself one of these. I'm sure if you do some Google searches that you'll be able to find a copy of this book. It's okay. I knew James Stewart personally. He used to teach at the school that I went to, and he's dead, so it's not like you're taking any money from him. And I'm more than glad to help anyone who comes to my office for help. You don't have to send me an email or something just to make sure I'm there, but I'm always available to help you go through problems if you want, and this will be the best way of doing it. Especially with integrals. There's really no... Do you know what I mean when I say recipe mathematics? Yes, okay, so this is the type of math that everyone sort of likes, right? Because it's just, we tell you how to do a problem, you go home and you practice it, and then we test you on that. Integrals really don't work that way. The best that we can do for integrals is say, well, here's an integral, here's a bunch of methods that we have, just try all these methods and hopefully one of them will work. So this is called the heuristic approach, right? So in order to gain some type of proficiency in solving integrals, that's only going to come with practice. So I encourage you to practice. Next, stop me in lecture if I say something dumb, right? Or incorrect, or both. If you have a question, I guarantee you that at least half the class has the same question. A lot of the reason I went very quick last week is because no one at any point stopped me for any clarification. So please stop me if I say something incorrect or if I say something that you're not following, because I'm more than glad to expand on those things. And in general, ask tons of questions. Just throw up your hand or holler at me. This needs to be sort of a more bi-directional type of conversation rather than me just sitting up here and lecturing to you guys. Okay, so that being said, let's start. So this is integration in a nutshell in one slide. Right? So the original question that we endeavored to answer was, well, if I give you some sort of curve given by a function f on the plane, right? So that's R2. The area under the curve is given by this integral, and we know that we can solve this integral using the fundamental theorem of calculus, right? That is, if the derivative of f, capital F is f, then we know that this area is given by big F evaluated at b minus little f evaluated at a. Right, and then you guys did a whole ton of practicing on single variable integration. You may not know, but integrals are very useful beyond just finding the area underneath a curve. For example, if you want to find the center of mass of an object, you take its integral. If you want to calculate the work done by a non-constant force, like Hooke's law, this is an integral. Most importantly, I think, is that integrals actually are giving you average values. Right? So the whole study of probability is basically applied calculus. Right? So if anything, calculus is crucial for the study of statistics and probability. And I hope you can understand how important statistics is in the Common Era. So here's an example. I actually wrote a whole book on this if you want to go purchase it. Or you can give me $1 and I can send you a PDF, right? Because that's about 100 times more money than I get from the publisher. If you ever want to make if you want to make not a lot of money extremely slowly, write a textbook. The best way to do it. So you don't need to know this, but I want to show you. Suppose you have some sort of function like this. And the function's a function of t, right? So time is on a continuous spectrum. Right? You can divide time as much as you want, but ultimately you're always able to pick a time halfway between any 2 points in time, right? So the fact that time is continuous means that we have to look at continuous curves, right? So if I give you a function which says, suppose you're waiting in line to get served, right? And I give you a function that says the probability that you're going to wait t minutes to get served is given by f of t. Right? If you want to answer questions like, what is the probability of me getting served between minute 1 and minute 4, you need to do an integral. If you want to answer a question like, what is the probability that I have to wait at least 6 minutes before getting served, you have to take an integral. So this is called the stochastic process in general, and it's very interesting if you go ahead and take some courses in probability, which I would recommend. Probability and statistics is probably the most important subject that you can study in university. At least that's what it seems to be, well, the case now. Big data is the big, I don't know, thing. If you want a job, study big data. Okay, so the techniques that we have for single variable integration are going to be crucial, and because to do double integration just means that we're going to do single integration twice. So I hope you guys are familiar with these strategies. So we can do integration by substitution, I hope. Well, yes, hopefully. That's what you should have learned last year. Integration by parts. You guys learned that? Integral u dv is equal to uv minus integral v du. I hope that is plastered in your head. You should repeat that to yourself 10 times every day, just so you don't forget it. Partial fractions. Yeah. Interesting enough, partial fractions is the only method you need to do all integrals, basically. If you ask a computer to do an integral symbolically, if you go to Wolfram Alpha or something, and you ask it to do an integral, what it will do is just make a really big partial fraction expansion, do it, and then bring it back. So in terms of computation, partial fraction expansion is the most important one. And do you know what I mean by table lookup? Okay, so another reason you need to find this calculus book, put this over here. I'm going to strive to use this document thing now so you guys can see it on the echoes. But you got to find this last page in here, in this textbook. Right? Because here it just tells you forms of integrals and what they integrate to. So in fact, here's integration by parts, right? Integral u dv is uv minus integral v du. But you should sort of recognize some of these when you're working through what you're doing. I was trying to do some of your problems from the other day, and I think you needed this one or something. So just keep in mind that if you're struggling with an integral, then in fact, maybe you should look at a table of integrals. In fact, when my father was studying this, they had sort of 200-page books, and the whole book was just these tables of integrals. But the ones that you'll need are typically in the back there. Okay, so this is what we mean by a Riemann sum. And we introduced Riemann sums. Well, Riemann sums are integrals, basically. But the idea is that if you want to find the area underneath this curve, you just pick a few points on the curve and construct these rectangles and take the areas of the rectangles, right? We may not know how to take the area underneath this curve, but we certainly know how to take the area of rectangles, right? It's the base times the height. If we half the width of these rectangles, you can see that we're going to get a better approximation to the area underneath the curve. And in fact, if we go more, we're going to get even a better approximation. And the idea, do I have one more of these? I do, is that if you take enough of these rectangles, really an infinite amount of these rectangles, then what you have in fact done is taken the integral. So when we do an integral, this is basically just notation for saying, look at this curve and take a sum of these rectangles and sum up an infinite amount of them, right? That definitionally is an integral. The fact that integrals can be done algebraically, the fact that we know that the integral of x goes to x squared half plus c, That's the fundamental theorem of calculus, right? Leibniz and Newton were both working on different problems, right? And they somehow realized that an integral and a derivative are related in this very fundamental ways, right? So that was an extremely important development. Okay, so we had several different types of Riemann sums, and they may have given you some questions as busy work to say, okay, look, we can take the Riemann sums using left endpoints, right endpoints, or midpoints. Does this ring a bell a little bit? Okay, so all that was saying is that if you draw these rectangles, and you want to break the interval that you want to take an integral underneath, right? So this is the integral of this function from here to here. You just want to break this interval into n many equal pieces, and then the point is we just have a few options as to how to take the height of this rectangle. Okay, so suppose we take the interval AB, and we want to partition that into 6 pieces. The points at which we take the heights are called sample points. Right? This is, again, related to probability. And we can place them anywhere in the subinterval. Okay, so here's an interval AB. I've partitioned this interval into 6 equal pieces, 1, 2, 3, 4, 5, 6. And this is what the interval would look like if we took left endpoints. If we took right endpoints, they would look like this, right? If we took midpoints, they would look like this. But the point I want you to take away is that it doesn't matter. It doesn't matter if they're left, right, or midpoints. All that matters is that you're taking a sample point somewhere from the interval itself. Right? So this is going to help us save a lot of writing, because I'm not going to say, okay, the third sample point is exactly 3 delta x's away from here. We're going to say, no, okay, take your interval, break it into n equal pieces, put a sample point in each one of those intervals, and it ultimately doesn't matter, right? Because these intervals are getting so small, right, that left, right, middle, it's all the same when the interval has epsilon width. Okay, so here's how we can write the integral using these midpoints. Okay, so I am going to take the sample points to be the midpoint just for this. Right? Here's our function f. This is our delta x. Delta is just a Greek way of saying change of. Right? So this is our change of x. And the distance between the width of this rectangle for the midpoints is the same as the distance between any 2 midpoints. But, again, the only important thing is that these points are taken from anywhere in the interval. And when that is the case, do you see how this sum in here is adding up a bunch of rectangles, right? So if the width, or if the base of this rectangle is delta x, and its height is given by the function itself evaluated at xi, right, then the area of this rectangle is given by f evaluated at xi times delta x, right? So this sum down here is just saying, just take the sum of each of these areas, the area given by this, and the next one, and the next one, and the next one. And as n goes to infinity, which means that delta x, right, the base of our rectangles are getting infinitely small, as this approaches infinity and the limit, then what we have done is define the integral. These two things are the same. This is just notation for this. Right? This is the Greek letter sigma, it's an E, but this is eta. Right? It's almost the same Greek letter, right? But they're chosen for very similar reasons. So when you see this, you can just think of this as a sum of an infinite number of things that add to a finite value. Okay, so here's the sort of more rigorous definition of the integral. Right? If f, so I'm going to teach you how to read these things. Let f be a real valued function which takes a real value and maps it to a real value. Let the closed interval a to b be a subset of the domain of f. Right? And I'm going to do what I said before. Just assume that we've divided this interval into n equally sized subintervals. And let's just say xi Klein or star is in the ith interval. Who cares about saying explicitly where it is? If we wanted to do that, we could. Right? Then, again, the integral from a to b of the function f of x, or the area underneath the function f on the interval a to b, is equal exactly to the sum of an infinite number of rectangles whose bases are getting infinitely smaller and whose heights are given by sample points on the function. Right? So that was basically last year in a nutshell. So double integration. So if we increase our number of variables by 1, what kind of object do we have now? Right? We had curves in space, curves on the plane. What do we have in space? Surfaces in space. So what is the equivalent question, or what is the analogous question to what is the area under the curve when we're talking about surfaces? Volume, right? What is the volume bounded by a surface, right? If I have some sort of surface, the thing underneath the surface is now a volume, right? Not an area. So here's a little bit of notation. The questions that you're given, so I've looked through this week's assignment, at least the multivariable calculus part, and they write intervals like this. I don't like this too much. I like this better, but it's important to understand that they're the same thing. Have you seen this notation yet? Ever? Have you seen, do you know what this means? Yeah, what do square brackets mean? Yeah, so that means you can include A. But the point is, this is just an interval on the number line. So you guys have never seen this cross? No, just a cross. Okay. So you guys weren't taught that much set theory. Okay, so I'm going to do this. Nope, this one. Okay. You guys know what a set is? Still hear me? Cool. All right, so a set is anything that has braces like this. It's just an unordered list, right? So if I put 1, 2, 3 in here, that's a set. And I can also have a set given by B. And let's say B is A, B, and C. If I put a cross in between here, right, this is called the Cartesian product. What does it do? Well, have you guys, you know what this is, right? The real line? Looks like this. What's this? Yes, it's this. It's the real plane, right? So this is a line. This is a plane. What's this? Yeah. Well, space. Space. Okay, but the point is, when I put a cube here, that was really notation for this. And this is really notation for this. Okay? So the cross product here, or not, the Cartesian product here means that you want to construct all pairs where the first element of your pair comes from A and the second one comes from B. Right? So for example, you'd have 1A, 2A, 3A, 1B, and so on through 3C. So this is why this notation is consistent, right? So if I have R, any real number, then R squared, or R by R, are all the pairs that you can make from real numbers, right? Anything here is going to be a pair. This triplet means that you choose 3 things, and you form a triplet. And a triplet falls into here. Right, so why am I telling you this? Well, if I have this interval, 1 to 2, and I cross it with another interval, maybe 3 to 4, what is the resulting set that you get here? Remember, a cross means that you have to construct pairs. You're going to be constructing tuples, where the first element of your tuple gets put in here, and the second order of your tuple gets put in here, right? So for example, 1.5, 3.5 is in this set. And so if I draw R2 like this, here's the interval 1 to 2. here's the interval 3 to 4. I'm saying 1, 2 cross 3, 4 means that we have to choose an x value between 1 and 2. Right, so somewhere in between here. And we have to choose a y value between 3 and 4. Somewhere between here. Right, so the point is, if I give you two intervals like this and put a cross in them, right, so this is equivalent to all pairs x, y, whoops, such that x is in the interval 1, 2, and y is in the interval 3, 4. This is going to define a rectangle in space, or on the plane. Any questions? This is pretty crucial. If you can't understand what an interval is, that this may be a wash, this whole lecture. Right, but anyways, right? So if you see this in your homework, right, you see a set that says all pairs x, y such that x is between a and b, and y is between c and d. This is just defining a rectangle. And the rectangles are going to have, what are the endpoints of the rectangle? What is the lower left side of the rectangle? AC. And what's the top right? BD. Right, so this is why I prefer this description, because it very readily gives you the shape of the rectangle. But again, don't get freaked out. It's just the same way of writing the same thing. Right? Mathematics is all about inventing 17 different ways to write the same thing. Okay, so here is the paraboloid 16 minus x squared minus 2y squared, restricted to the rectangle, or in this case, square. X is taken from 0 to 2, and y is taken from 0 to 2, right? So you can see that rectangle in the base here. And this is the volume that is sort of given by that surface over this region. So the question is now, how can we estimate the volume of what this picture is? So when we had an area of a curve, we divided that area into little rectangles. Now that we have a volume, what can we divide the volume into? Rectangular prisms, right? The point of a rectangle was that it was super easy to calculate its area, width times height. A rectangular prism, just a prism that's rectangular, is width times height times base. It's the area of the thing at the bottom multiplied by the height, right? You want that area at all these levels, right? But the point is, again, it's going to be super easy to get the volume of a prism. Okay, so here is one approximation. I didn't do the one prism because that's kind of boring, right? So if I took that region, that square region 0, 2 to 0, 2, and broke it up into 4 pieces, then here is an approximation of the volume. Right? We have one prism here, one prism here, one prism here, one prism here. They each individually have a volume. And if we add them up, we're going to get an approximation of the volume under the curve. So is it an under approximation or over approximation? Under approximation. And in this picture, you see I'm taking this endpoint here to take the heights. And the same thing is going to happen as what happened with these 2D Riemann sums, right? So here's one approximation, here's another approximation, and another. Is there one more? Yeah. Right? So as we keep doing this, we're going to get better and better approximations to the volume of that surface. And again, in the limit, we're going to get the integral, or what we call the double integral now. Okay, so here's a little reminder of how to take the volume of a prism. So remember, in the 2D example, we took an interval on the real line and we divided it up into n equal pieces. Now that we're working in 3D, we're going to have to take a grid, right, the thing on the bottom, and divide that into equal pieces, right? In this case, I've done an equal amount of divisions in y and x, but generally the regions on the bottom can be rectangles if you wanted. They don't necessarily have to be square, right? If I divided this region into 3 and this region into 2, we wouldn't have squares. Again, the important part is all we need to know is how the plane down here has been divided. And then from each of these divisions, each of these rectangles, we have to choose a sample point. And then this sample point gives us the height of the prism, right? So this point up here is x-cline, y-cline, f evaluated at x-cline, y-cline, right? Because you have to imagine that there's some surface over here which is touching this point. And then we want to take delta x and delta y and make them smaller, right? The same way that we're taking rectangles and making their bases smaller. We're taking prisms and making their bases smaller, right? And as their bases get infinitely small, we're going to get a V integral. Okay, so we can form the integral by adding the volumes of rectangular prisms with progressively smaller bases, right? I could have given you a 2-hour lecture on this, but there's no real point, right? Because no one would ever take an integral by doing a Riemann sum, right? At least symbolically. It would be impractical to do a limit, right? We want to use all the algebra that was developed last year, right? With the caveat that if you're doing something on a computer, if you want to do a numerical integration, then these Riemann sums are important. Okay, so when we had an interval on the line, right, we had lots of options for where we could take our sample point, right? Or at least we had some options for the extremes. We had a left extreme, a right extreme, and a middle, even though ultimately we could choose anywhere from in the interval. But what are the similar options for intervals on the plane? Right, so what are the extreme values on a rectangle? So I write a question last year, and I say, okay, to calculate this Riemann sum, do it with left interval, right interval, and then in the center. Right? If I give you a square, what does it mean if I say go left? It's not a trick question. I know maybe you guys think I'm always here to trick you. I will tell you when I'm trying to trick you, as a warning. Usually just on your final. But the intervals, the endpoints on a rectangle are just top left, bottom right, top right, and the center. Right? So you could get different types of approximations of the volume, depending on which corner you take. But again, it's all pointless, right? Because again, all we care is that we have taken the sample point somewhere from this rectangle. Right? So again, take your plane, divide it into equally spaced rectangles, choose a point from each of those rectangles, it doesn't matter, and sum up the resulting volumes, and that is what we call our Riemann sum. And we'll go through an example, but theoretically, it's not that difficult. Okay, so you guys are familiar with the integral on the left here, right? So there's a lot of hidden things in this integral. Because we're taking the integral with respect to dx over here, it's implied that this AB interval is taken to be x. This really means integrate from x equals a to x equals b. Right? We just left it out because that's sort of implicit here. But I could also write the integral like this. Right? What is the integral of f of x over this region, or this interval on the line? And I say this because I don't want you to be surprised when I write this integral. Right? So this looks complicated, but let's decompactify it because it's just a codification of what we've been talking about. Right? So this is the definition for a 3D Riemann sum, which is just a formal way of saying let's take an infinite number of volumes of prisms and sum them. Okay? So if you give me f, and this time it's a real function defining a surface in space, right? You give me 2 points and I give you one back. And it's defined over a rectangle, right, in xy. And assume further that this region, this rectangle, has been divided into n by m many equally sized subrectangles, right? So that is, you take AB, cut it into n pieces, and take CD and divide that into m pieces, which means you're going to have n times m many resulting rectangles. And we'll illustrate this later. Then, just choose some sample points from within those rectangles. It doesn't matter which. Then, the double integral over this rectangle, R, right, the same way it was over this interval here, is defined to be the sums of those prisms as we take the bases of those prisms to be infinitesimally small. Right? Or another way of saying it is, after dividing the region in the xy plane into an infinitely many subregions. All right, so let's do a practical example. All right, so this may be something you see, I don't know, I don't write your midterms or exams or assignments, right? But this could be fair game on any of those, although there is no Riemann Sums on WebAssign. But anyway, so suppose there was, I took this right out of the story. Estimate the volume that lies below the surface z equals xy and above the rectangle which has x values 0 through 6 and y values 0 through 4 by dividing the x interval into 3 and y interval into 2 subintervals respectively. And for the sake of this, let's just choose midpoints, right? Although I've been stressing that it really doesn't matter where we take them. Okay, so let's do this. Okay, so the x values go from 0 to 6. And if we want to divide 0 through 6 into 3 subintervals, then we're going to have to step by 2, right? So 0 through 6 in 3 subintervals is the interval 0 through 2, then 2 through 4, then 4 through 6, right? That's 3 pieces. To divide 0 by 4 into 2 pieces, well, that's 0 through 2 and then 2 through 4. So in the end, all we're going to have to do is construct this sum. So this, you're comfortable if I switch notation like this? So this is still a double sum, right? Because you have, I'm saying you have to take midpoints from a bunch of sets. But anyways, it'll be clear in the end. So I need to take the sum of 4 times x times y, right? This 4 is this delta x times delta y, right? That's the base of our prism. And x times y is the height of the prism, right? Only because that's how the function is defined, right? So all we need to do is this sum here, right? So as long as we can determine the midpoints, then we're done, right? Then we just have to write down the sum. So typically, the most difficult part of these Riemann sum questions is just determining the interval. Okay, so here's our region on the plane, right? There's a surface coming out, right? It's being defined over this. Right? So here's x equals 0, y equals 0, and here's x equals 6, y equals 4. So how many regions did I want to break x into? Is it 3? Right? So there are 3 intervals, right? Each 2 units wide. So here's the x interval, here's another one, and here's another one. Right? Here's the y interval broken into 2 pieces. Right? So there's 1 piece here and 2 pieces. So these are our subrectangles, right? So these are going to be the bases of our prisms, right? So where are the midpoints? Well, they're here. 1, 1, 3, 1, 5, 1, 1, 3, 3, 3, 5, 3. Right? You can see that each of these points are 2 units away from each other in any direction, right? So from here to here is 5. From here down to here is 1. So all we have to do now is take our collection of midpoints, right? 1, 1, 1, 3, 3, 1, 3, 3, 5, 1, 5, 3, and just do this sum, right? So the sum of 6 times x times y, as x and y are from the collection of midpoints, and we just work this out to 4 times 36, which is 144, right? So that would be the answer to this question. Why is there which 6? 6, that should be 4. Yes. Yes. I think I just didn't change the top one. I always say I should number these slides so I can find them, but I never do. But thank you. You're paying attention. This makes me feel a lot better if you catch my mistakes. You should know that I put them there on purpose, these mistakes, just to make sure that you guys are paying attention. So 6 bonus points to whoever pointed that out. Bonus points do not equate to real points, but you can feel good for having them. Okay, so why have we been doing this, right? We're never going to do integrals using the Riemann sums, right? It's the same way you would never do integrals using Riemann sums in the 2D case. This is why we have the fundamental theorem of calculus, and that's why it was so fundamental, right? Because it allowed us to very rapidly take integrals. And this is wrong as well. This should be iterated integral. Enables us to algebraically determine a double integral by doing 2 single variable integrals using the myriad of tools developed for doing so. Right, so last year you spent a lot of time learning all of the strategies for taking integrals of single variable functions. No surprise, a double integral is just a single integral done twice. So you don't really have to learn new techniques. You just have to apply the old techniques one after another. Right? That is to say, we're going to be iterating single variable integrals. And iterate means to perform repeatedly. Right? So a triple integral will just be 3 single integrals, and so on, so far. Right? That's where the word iterated comes from. All right, so here's the definition. And I promise I've put tons of examples in this, which we'll do afterwards. And I've tried to make them similar to your WebAssign. And so, mainly so I don't have to answer 100 emails. If Bjorn wouldn't get mad at me, I would just sit here and do your homework for you, send you on your way. You'd all think I was the best professor for giving you the answers. I wouldn't have to deal with any of your emails. Maybe I will just do your homework after this class. Oh, yeah. I do want you guys to pass. Yeah. I've been thinking a lot about how I can best teach you to, so you get, because you want high grades in the class, right? What's more important, to get high grades or to actually understand the material? I'm asking this seriously. When I went to driving school in Canada, we have cars in Canada. You may not know. But they're like, we're not going to teach you how to drive well. We're going to teach you how to pass the driver's test. Because that's really the only thing you're interested in. So I've shifted gears. I think I've been giving you too theoretical of a presentation. So I'm going to give you less of the theory and more of the practice. But you still need to know the theory in order to, succeed at life. Right? Because when you go out to these engineering firms, they're going to actually ask you to answer questions. Right? You're not going to have a recipe for answering them. Right? It doesn't seem sensible that you would be employed. The employer would hand you a sheet of how to solve all the questions that they want you to answer and to send you on your way. Like, they're going to give you questions that they don't have the answer for. Right? So a lot of people always ask me, what's the point of studying mathematics? And perhaps the content, in some sense, aren't that important. But it's just the delivery. It's just a mechanism for teaching problem solving. And problem solving is more important than actually learning how to integrate. So I'm going to try to meet you guys halfway. But again, practice and come to my office and I will help you practice. It's really the only way to gain proficiency. And those of you who obtain the best math competency will get paid more in jobs. Right? So here's your financial incentive for becoming good at math. Right? You'll get the better job. Is there any biologists in here? I usually like ragging on the biologists, but since we have one. Because you can't memorize your way through this course. That's what I call the biology approach. Oh. I'm tired. Okay, so here's the definition for an iterated integral. So I give you a rectangular region from A to B, across C to D. And the function is defined for that region. Then we can calculate this double integral over this region, right? The volume given by this function over this rectangle by performing 2 integrals, right? So we have to be careful here. The order that this is written is important, right? So this is the integral from A to B with respect to x of the integral from C to D of f of x by y, right? So you have to do the inner integral first and then the outer integral second. And if we think about what this is saying, right, remember, integrals are just infinite sums. So the inside integral gives you what? An area, right, which is like adding together a bunch of lines. And then when you have an area, you're adding together an infinite amount of areas, right, like slices, which is a volume, right? And if you want to think harder, you can take a volume and slice it in time, and that would give you a triple integral. Right? But the point is, this is how we're going to calculate the volume of solids, just by asking what their cross-sections look like and integrating like that. But this is the secret sauce, right? Because we know how to do integrals of one variable. So you have were you giving me a 2D example or a 3D example? Okay, so with 3D, you have some surface. So imagine like a pyramid with a square base. How can I get the volume of that pyramid? Well, you look at you go to the bottom of that pyramid and you make a slice, and you get a rectangle, right? And it has an area. Then you move up one, and you get a different rectangle, smaller, calculate its area. And as you do this, as you make a collection of these smaller and smaller rectangles, what you're going to form is the volume of the pyramid. I don't know if that answers your question. No. I'm not going to give you guys a break. You don't deserve a break. Breaks are for winners. Yeah. Maybe the biologist can have a break, because I kind of ragged him. I feel bad for teasing you. Yeah. Yeah, this is why we developed partial integration in the first place, right? So whenever we are doing things in two directions, it's typical just to say, just make one of those directions constant. Pretend it's not moving, right? So whenever we take something to be constant, so in the plane, if I said y is equal to 7, that's a line. In R3, that's a plane, right? So whenever you set one variable is a number, you're cutting it by the version of its line in that space, right? And it will always bring you one dimension down, right? Because if I put y is 7 in here, what you're left is with the function in x. Okay, but let's show you how this works in the real world. Oh, but first let's talk about an Italian. Houdini, mathematician, presumably Italian. I don't know what he did. I should have learned. I'm more interested in, mathematicians have seriously interesting lives. They either kill themselves, one another, or just go crazy in general. I'll talk to you about Galois at a later date. Okay, but he proved, and it's actually not that easy, that you can switch the order of the integrands. Right, so on the left, we have the integral from a to b, integral from c to d of x dy dx. That is, you do the y integral first, and then you do an x integral. Or you can do the integral from c to d of the integral from a to b of f dx dy. Right, so in the right-hand side, we can do the x integrand first and then the y integrand. Right, this is only true for rectangular regions. At least that's what Fubini proved. So this is important because sometimes switching the order of the integrands will make an integral that was impossible into an integral that was possible. These are the heuristics that I'm giving you. If you're doing a double integral and you're having a problem, say, okay, what happens if I permute the order of these integrands? Just add this to your toolkit. Okay, so here, I think this is very close to a question on your homework. Kind of close. Okay, so how can I do this? Right, so let's interpret this question. I'm giving you a rectangle, and I want the volume given by that surface over that rectangle. What do I do? What's the first step here? This is on your homework, right? And I've already told you how to do it. You guys look at that. What do I do? Okay, what does x go over? 0 to 2. That means y goes from... So is this correct? Yes, right? Because this one matches with the inner one, and this one matches with the outer one. Right, so this is saying take x from 0 to 2 and take y from 1 to 2. This is a typical mistake often I find students make. Right? But remember, we have to do the inner one and then the outer one. Okay, so this should now be standard practice. Right? So how do we take, what's the integral of x minus 3y squared by y? Oh, let's do it in pieces. What's the integral of x by y? xy. Right? And what's the integral of minus 3y squared? Minus y cubed. Yeah. Okay, so I'm going to repeat myself. The integral of 1 to 2 from x minus 3y squared dy, right, is this. So you don't have to put Do you know what I mean when I write this? Okay, it's not typical to write y equals 1 to y equals 2, but since we have two directions now that we're working with, x's and y's, I'm going to put them in just so we don't get confused. And I would recommend that you do it too, until at least you get comfortable with working with these type of computations, because it is easy to get mixed up. Right? Because now that we have to evaluate this, we have to remember to evaluate the y's and not the x's. Right? So I always remember to myself, it's always top minus bottom. So what's this evaluated at the top? Okay, so this is 2 times x minus 8. And on the bottom, we're going to have x minus 1. Did I do that right? Yes. So it's going to be 2x minus x is x. 8 minus 1 is minus 7. Did I do that right? Minus, this may be wrong. No, this is wrong. So this should be minus 8 minus 1. So that should be 7. Yes? Okay. So this means the next thing's going to be wrong too, but we'll cope. Okay, so that's the inner integral. Now we have to do the outer integral. All right, so I'm just going to put it. So here was the original question. We've now solved for this thing on the inner. So we now have to go from 0 to 2, x minus 9 dx. So what's the integral of x minus 9 by x? X squared by 2 minus 9x. Perfect. Right? And again, we have to take this from x equals 0 to x equals 2. So top minus bottom, top minus bottom, top minus bottom, top minus. Just remember that, right? So top is 4 halves, which is 2. 2 minus 18 is minus 16. And the rest is 0. So this should be minus 16. Hooray, except it shouldn't, right? Because this wasn't supposed to be a 9. Right? But okay, I'm off by a constant. I'm correct modulo my errors. I usually wouldn't remove marks for something like this. But you should be careful. But I care less about these arithmetic errors than just sort of really severe misunderstandings of the material. You want to do a substitution here for the second one? This does not require a substitution. It's probably the Oh, after, as in we remove these bounds? Like we do the unbounded integral, the integral without the numbers? Should give you the same thing. But it'll make things a little bit harder, right? Because things can, when you put numbers in, it's going to simplify. Well, the constants all cancel, right? Because the constants, you'd have to include, if you want to give the unbounded integral, then you'd have to include a constant. Right? But the answer to your question is yes. It would be okay to do both of the symbolic integrals and then to put in the bounds at the end. Right? But I wouldn't do that because it makes the computations more difficult. Because especially here when you have a 0, right? You want to really exploit zeros. You want to make things real simple. Okay, so here's an exercise for you guys. Reverse this and determine, or reverse it and prove that you get the same answer. Of course, you'll have to correct my mistake first, right? Just to confirm that Fubini's theorem works. This one's very close to one of your web-assigned questions. I put it on here deliberately. Okay, so one of your web-assigned questions looks pretty much identical to this. So what would you do? What's the answer? Or what's the first step? Yeah, do the inner integral, then do the outer integral. So what's the inner integral? Are you looking at the solution? Or did you work it out already? Okay, well, how would you approach this if you just seen it? And the answer's on the board for anyone who wants to venture a guess. You could try doing it by parts. That was my first inclination. Let's do substitution. Who said substitution? That is just a marvelous idea. What's the substitution here? Yeah, right, because if you take the derivative of x plus y squared to the 3/2, the 2y is going to fall out of it. Chain rule makes this a lot easier. Right? Try by parts, that's what I did, and then I'm like, oh, this isn't going to work. I should try something else. And this is the sort of heuristic approach. When you do an integral, you have to try something and then fail, and then try something else, and then fail again. Then try something else, cry, and then write your professor a panicked email, like a few minutes before your homework's done. That's how I learned calculus. Okay, so how do we complete the substitution? So what's du in this case? Du itself, right? So how do we do a substitution? What are we going to have to replace to do this substitution? We're going to have to replace dy. So we want to know what the derivative of u is with respect to y, right? So du is equal to 2y dy, because the x goes away and the y falls out from chain rule, which means that dy is equal to dy over 2y. Okay? So if I substitute dy in for here, and I substitute u in for this, what am I left with? Well, I'm left with this. And this is why I'm also going to put the equations for the boundaries here. Right, I want to take the integral, so I'm going to do the inner integral first. The integral is y equals 0 to y equals 2 of y root x plus y squared dy. So remember when you're doing a substitution that you also have to change the boundaries. A lot of people forget this. But the boundaries are easy, right? So when y is 0, u is x. When y is 2, u is x plus 4, right? We're just utilizing this equation over here. Then I'm going to put my u in here, right? So this is what we're substituting. And I'm going to replace my dy by du over 2y, and we can strike out those y's, right? That's why substitution here was the right method. So getting rid of these y's, we're left with what? 1/2 integral u equals x to u equals x plus 2 squared root u, right? And what's this integral now? What's the integral of root u, u? Okay, well, this is u to the power of 1/2. So how do I integrate that? Almost. Oh, you say over 3 on 2. Okay, so or 2/3 x 3/2. Okay. Right, so this integrates to 2/3 u 3/2. And we want to take this as u goes from x to u goes to x plus 2 squared. Right? You'd know something's up here had you not fixed the limits, right? Because then you'd have some sort of function without x in it, right? Which is suspicious. Okay, so after I do top minus bottom here, we're going to get 1/3 x plus y squared, right? That is the top part. All right, is that wrong? Oh, sorry, I'm just putting u back. Okay, so from here to here, I'm just putting u back. So u is x plus y squared, so that goes here, x plus y squared to the 3/2. I can take that 2/3 out, but I don't know why it became 1/3. Maybe that should be a 1/6. Well, I have 1/2 and I have 2/3. I think I wanted to take the 2/3 out, which means, oh no, 1/2 plus times 2/3 is 1/3. Sorry, I'm losing it, right? These two cancel. I know how to multiply fractions. Don't anyone tell me that I can't. I have 3 diplomas in mathematics. I can multiply the hell out of fractions, except in this case. Okay, so you have 1/3 x plus y squared to the 3/2, and I've just changed this. So when u is x, that means y is 1/2. When u is x plus 4, that means y was 2. So I do top minus bottom here, and you're left with 1/3 x plus 4 to the 3/2 minus x minus 0 to the 3/2. Simplifying that down, you're left with 1/3 x plus 4 to the 3/2 minus x to the 3/2. Okay, so now we have the inner integral. Right, so again, we did single variable calculus once, and now we have to do single variable calculus again, right, for the outer integral. Right, so I just put the thing we just computed on the inner integral, and now let's do this, right? So this one should be easy. Right? This is more or less a polynomial. Well, it's not a polynomial, but it's an expression in x with rational coefficients. So we take this. The integral is what? Well, I have to add 1 to here, so 3/2 plus 2/2 is 5/2. If this 5/2 gets put down, we have to cancel it, so that's how that 2/5 gets here. And the same thing for the x on the other side. And then we have to take this expression and do top minus bottom, right? So evaluate this at 3. And so there's a 7 here, there's a 3 here, and subtract the evaluation of it at 0, which is easy. We like zeros. And in the end, we get 2/5, 7 to the 5/2 minus 3 to the 5/2. And yes, this is the preferred answer. Right? Because if you put this through your calculator, you no longer have the answer anymore. Right? You have an approximation of the answer. Right? So if I'm asking you for an answer, give me the answer. If the answer is the square root of 2, that's what I want to see. I don't want to see 1.4, right? Because that's not the answer. Right? It's an approximation to the answer. This isn't physics. We care to be exact in mathematics, right? No spherical cows. Remember spherical cows? You guys are, no one's familiar with spherical cows? Thank you. Thank you. That's what they do in physics, right? If they want to model something, they have to make it very simple. So if you want to like model a cow flying through space, the first thing you would do is assume that the cow is spherical. So you just have these spherical cows flying around. Don't laugh. That's actually, well, in the grand scheme of things, a cow and a sphere act pretty similar in the grand scheme of things. Except one is more delicious than the other. Delicious spheres. Okay, let's do this one now. This is very easy, right? Because you're given the rectangular regions are easy because you know how to integrate. It's when we're not working over rectangular regions, which is going to be complicated. You guys still with me? I don't want to give you a break because I imagine you'd all just rather leave earlier. Yes? Okay. I'll let you guys leave earlier. Okay, so let's just quickly go through this one because it seems like you guys are following. But again, a double integral is just doing single integral calculus twice. Okay, so let's calculate the integral of y sine xy as y goes from 0 to pi and x goes from 1 to 2. Okay. Let's channel our Italian friend. What should we do here? Who said that? Bonus points. 100 bonus points. Why do we want to switch? What integral is going to be easier? Well, if we integrate y sine xy with respect to y, that's at least going to require integration by parts, because there's a product. If we look at this function as a function in x, it's just sine x. We know how to, that's easy to integrate. And so this is an example of where you should swap the order of integration because it's going to be easier. In the end, I actually can't recall. Like, it would work. You could do an integration by parts first, right? Well, if I took the derivative of sine xy, you're going to get minus cos xy. You're not going to get a y falling out of that, right? Because x is a constant. Or you're going to get 1 falling out of that. The derivative of xy with respect to y is x. Sorry, so you're going to get x falling out of it, which is still a constant in this case. But anyways, give it a try, right? Just to confirm Fubini's theorem and to get some practice, right? So notice that the integral from 0 to pi of y sine xy dy is hard. At least would require integration by parts. But the integral from 1 to 2 of y sine xy dx is relatively easy, right, relative to the other option. Right? So what is the integral from 1 to 2 of y sine xy dx? Right? Remember, y is a constant. Right? So the integral of sine goes to what? Minus cos. Right, so you get minus cos xy. I do that right? Right, because if you took the derivative of this, you would get sine xy times y. In that case, it's helping us. Okay, so then we need to take minus cos xy from x goes to 1 to 2. So that's minus cos 2y plus cos y. I may have reversed it. Yes, right? So cos y minus cos of 2y. Now we have to do the second iterated integral. So that's going to be the integral from 0 to pi of cos y minus cos 2y, the result that we have from the previous slide. So what is the integral of cos y with respect to y? Sine y. What's the integral of minus cos 2y with respect to y? Sine y half. Right. There we go. Now we have to take this equation and evaluate it at pi and subtract the evaluation at 0. So what is sine at pi? Oh, fight. Goes like this, right? Starts at 0, peaks at 1 at pi half, hits 0 again at pi. Okay, so the first one is 0. Right? Sine of pi is 0. What's sine of 2 pi? That's 0. Okay, so the top summoned is 0, and now I have to subtract the bottom. So what's sine of 0? What's sine of 0 by half? So the answer is how tremendously unsatisfying. Right, but if we were to plot this, right, you would see that you have a surface that's going above the xy plane and underneath it. Right, so this is, maybe I should have mentioned this, but it's signed volume. Right, volume underneath the xy plane is going to be negative. In the same way that you had area underneath the real axis that was negative. Right, so if you took the integral of sine from 0 to 2 pi, you'd have this positive area plus this minus area. Right, that's why the area under the curve is considered to be 0. So it's just the 3D version of that is happening here. We have some surface that's moving through the xy plane and giving us both negative and positive values. Next week's going to be interesting because we're going to get to well, I think it's fun. We're going to determine what the volume is of all of these Platonic solids. Have you ever been curious like why the volume of a sphere is 4/3 pi r cubed? No, none of you have been curious. Get out of my classroom. You don't have the light of inquiry required. Well, I thought, so like next week we're going to determine the area of a circle and sphere, maybe even a hypersphere. Oh, it's going to be a riot, guys. Bring beers. Moral of the story: sometimes a double integral is easier to calculate when the iterated integrals are swapped. Okay, so this is where things get a little bit more complicated, right? This lecture would have been kind of boring if the moral was entirely just do a single variable calculus twice and game over. This was easy because the regions that we were taking our integrals over were simple. A rectangle is really the simplest type of region that you can express in Cartesian, right? You just needed to give me 2 endpoints of the rectangle. Right, so we had this definition, right, that the double integral over a rectangle of f is equal to just doing these iterated integrals, right? 1 over x and 1 over y, right? Because basically, if I told you that we are here, I know that y moves from here to here. If I'm here, I know that y moves from here to here. We're always moving right through the same region in y. What about regions like this? If I just give you some sort of blob, which is the mathematical definition or term, on the plane, what is the volume that is above this region? Right, we're in R2 now. We're in a plane. We can make much more complicated intervals than we could ever do on the line. There's really only one thing that we can do on a line. We can put a point on the line or we can bracket on the line. Right, but there's infinite amount of domains that we can draw in R2. Any ideas? Good, because then there wouldn't be anything for me to teach. Okay. So it entirely depends on the region D. In the very least, we need to know a mathematical description of D, right? I can't just draw something. Well, actually, there's something called a planometer that you can, there's like an actual device which you can roll around, but let the engineers teach you about that. There are two types of regions, type 1 and type 2. I don't like those names, but that's the names that they've given in the Stewart calculus and they've given on your homework, so I'm going to use them. A type 1 region means that you know specifically how your x is moving. Right? So this is type 1 because x is moving from A to B. And again, so if I move from A to B and the region is given like this, that I know what the bottom, like I have some sort of function which tells me where to begin, and I have some sort of function to tell me where I end. Because I need to know if x is somewhere in this region, say here, that I need to take an integral from y equals this point to this point, which is different than if I were to move here, where I need to take the integral from y equals here to here. Right, so the name of the game is, if I tell you where you're integrating with respect to x, can you tell me where to stop and end on y? Right? That's what a type 1 region is. Right? A rectangular region in x with a region in y that's given by two functional endpoints. Okay, so this is a type 1 region. This is also a type 1 region. Right? Because if I go somewhere here on this x, I know that I start here and end here. There's a description for this. This is just a parabola rotated. Or in this case, it's the positive root x and minus root x. This is what we call an enclosed region, right? If you give me two lines, right, and you write them on the plane, sometimes they're just going to naturally bound a region like this. If you took minus x squared, shifted up, and positive x squared shifted down, you're going to enclose the region. So if you see on your homework or in your books them talking about a region enclosed by two functions, this is somehow what they mean. This is another type 1 region, but you have to be careful, right? Because the region description of D1 is different than D2, despite the fact that the functions that describe them are the same functions. You always need to know where to start and where to end. Right, so we start here on G and we end on H, but on this side, on D2, we start at H and end up at G. Okay, so this is another common mistake that students make. They forget to account for these intersection points where the things have actually flipped. Right? Okay, so type 1 region. A type 1 region is a region D instead of R. R was for rectangle. D generally just stands for domain. In R2, right, so on the plane, is the points x, y such that x is taken in the interval a to b, and y is given on the interval g1 at x to g2 at x. Right? So that means you have to pick an x first, right? And then it tells you what the y's can be. And so type 1 means that x is known explicitly. One of the two regions has to be rectangular. The type 2 region, spoiler alert, this is switched. Same thing but rotated. Proposition. If f is continuous, right, that is no holes, no trending to infinity, on this type 1 region, then the double integral over d of f at dA, right, this is just, oh, there shouldn't be an equal here. Whoops. Right? This is defined to be this integral. The integral of f with respect to y, as y goes from g1x to g2x, and as x goes from a to b. Right? So pick an x, do this integral. Right? Again, we're just adding together areas. So these are very typical of the questions that you're going to be given on web assignment, homework, test, quizzes. Most of the effort is going to come from actually determining your endpoints. You should be pretty comfortable with single variable calculus. So what is the region bounded by 2x squared and 1 plus x squared? Well, what kind of shape is this? And what kind of shape is this? Parabola shifted. Okay, so you should draw it. Right? And when you draw it, you get this picture. Step one in these questions is always just draw out your region and be mindful of where they intersect. Right? So here's the top parabola. Here's the bottom parabola. And they have endpoints here at -1, 2, 1, 2. And so this is important because it tells you what your x's range from. Right? The region that's enclosed here starts at x equals minus 1 and ends at x equals 1. And otherwise, you're not enclosing anything. Right? You're open-ended. You'd have to move to infinity. Right? So these weren't explicitly given, but they are determined by those intersections. And then once we have the endpoints for x, we know that y is going to go from 2x squared from the bottom to 1 plus x squared on the top. So thus, the region D are the set of points x in the interval minus 1 to 1, and y in the interval 2x squared to 1 plus x squared, right? It's always least to greatest. Right? Smallest thing to largest thing. And otherwise, it's not empty. The interval from 2 to 0 is empty. There's nothing in the interval from 2 to 0. There's lots of stuff in the interval from 0 to 2. Okay, so let's actually now do this integral. Okay, so we want to integrate the double integral of x plus 2y dA over this region D that we illustrated on the previous page is equal to this. Okay, so it's the integral of x plus 2y, taking y from 2x squared to 1 plus x squared, and taking x from minus 1 to 1. Resist the urge now to employ Fubini's theorem. We don't have a rectangular region. Right? It doesn't apply here. Okay, so knowing this, what is x plus 2y? What is the integral of that with respect to y? xy plus y squared. Perfect. Right, so again, we just do the inner integral. It's xy plus y squared. We have to take the endpoints y equals 2x squared to y equals 1 plus x squared. Like, this is why I prefer keeping these around, so we know exactly what we're evaluating it at. When we evaluate this, it ends up being this. Let's see if I did it right. So that's x times top, 1 plus x squared, plus 1 plus x squared squared, minus x times 2x squared, plus y squared, which is 2x squared squared. Okay? Let's see how I simplified this. Oh, I just skipped all the steps. I hope you're okay with this, though. I can't do literally every computation. So once you do that, you get a polynomial. Polynomials are super easy to integrate. So we get that. I'll leave it up to you to double check. And then we do our top minus bottom again, and we end up getting 32/15. Hooray. Very similar to something that you'd find on your homework. Let D be the region enclosed by, it's another way of saying these, the line y equals 0 and y equals root 4 minus x squared, and evaluate x squared y. What is our first step? Draw a picture. Determine the region. So what is this? What's y equals 0 in xy? Yeah, this line, the x-axis. What about y equals 4 minus x squared? What is the graph of y equals square root 4 minus x squared? Try again. Nope. Not a parabola. Let's square both sides of this. What do we get? We get y squared equals 4 minus x squared. It's a circle, but not quite. What's true about y in all this case? Can y be negative? No. Right? So y always has to be positive. Who said top half of the circle? Sorry, you're right. 200 bonus points. Right? So I thought somehow it was rotated a bit, but then I explained it away. Okay, so here's our y equals 0. Here's our top half of the circle. We know that these intersect between, we know this intersects at minus 2, 0 and 2, 0, right? Because this is the circle of radius 2, which means our endpoints for x are minus 2 and 2. And we move from y equals 0 to root 4 minus x squared, right? So here's our region. D are the collection of points, x, y. X goes from minus 2 to 2. And y starts at 0 and ends at 4 minus x squared square root, depending on what x we're choosing. Okay, so again, now we're just doing single variable calculus. There's the original question. This is what it looks like when I put in those boundaries that we just calculated. First, we have to do the integral with respect to y, so xy squared becomes xy cubed over 3. Then we have to do top minus bottom, which gives us this. I don't think it's necessary to expand this, but let's see what I did. I said this is x form. Yep. So this is 4 minus x squared to the power of a half. Something to the power of a half to the power of cubed is 3/2, Gesundheit. And then we just have to evaluate this. So how can I integrate this? That. Well, okay, this one should be pretty easy, right? Because if I take the derivative of 4 minus x squared, you're going to pop out an x. Right? So this x is actually, it's good that this is here. If this x wasn't here, we'd be in some trouble. But anyways, use your powers of single variable calculus. Is that 20 after? Yes. We take this, we integrate it, we get minus 1/5, 4 minus x squared to the 5/2. Is there anyone who wants me to show how that was done? No? Okay, cool. So I'm going to assume now that we basically know how to do single variable integrals. And then we just complete it. Oh, it's 0 again? Yeah, I guess you're going to get 4 minus 4 and 4 minus minus 4. Yes. Let me write it down. Ow. In every other lecture hall I've ever taught in, there's always been a chair. So that's why I have to drag this table over here. I'm not crazy. Necessarily. Yet. So the question was how we did that inner integral. So this was the integral x 4 minus x squared. 4 minus x squared. Oh, I can look up. That's dx. There's 2 of these, but you can never only show one of them. Why is there 2? Doesn't make any sense. 2 of these. Is there? Well, how come I can only show 1? I only have a PhD in computer science. I don't know how all this stuff works. Okay, so this is what we wanted to do, yeah? Yes? Okay. So when I look at this, I'm basically saying, okay, well, what happens if I increase this by 1, right? So you're going to get 4 minus x squared, 3/2 plus 2 over 2. That's 5/2. If this 5, so now I have to think, how can I reverse this, right? When I take the derivative of this, it better end up being this. So if I take the derivative of this 5/2 is going to be subtracted by 1. So you get 5/2 minus 1 gives you 3/2. So that, the bounds work out fine. But this 5/2 is going to be multiplied out front. So I need to get rid of it. Yeah? And from product rule, something's going to come out of here as well. Minus 2x is going to pop out of this. Well, I can use the x, but I don't want the minus 2. That should give us minus 5th, 4 minus x squared 5/2. I'll just prove it to you. Let's just take the derivative of this, and I'll show that we get what we're integrating. So if this is f, then f prime is what? Minus 1/5 times 5/2, 4 minus x squared 5/2 minus 1, which is 3/2, times the product rule, or sorry, chain rule, which is minus 2x, which is what? So this 5 cancels with this 2 cancels with this, and so do these minuses, and you're left with x, 4 minus x squared 3/2. Okay. So that's how I do integrals. I'm basically just thinking, I'm just trying to construct something which ends up having a derivative equaling the thing I'm trying to take the integral. That may seem like the most obvious statement, but that's how I do it. And it just requires a bunch of practice. Integration is sort of, I don't know, we just use computers to do integrals. Yeah, you could do substitution, but you should become so good at substitution for questions like this that you shouldn't have to use it, right? Because, yeah, you should get intuition. The truth is that you're going to forget all of this stuff the instant you take the final. It's like a joke among mathematicians that none of us remember how to do multivariable calculus. It's like we never I've never used it. It will be the first math that you basically will be taught all of. And at the end of, when I learned at the end of vector calculus, they're like, okay, that's it. That's basically all that we have figured out about calculus, and that's all that we need. You have now finished calculus. Right? So that was very satisfying. I failed that class like 6 times. But in Canada. It's like an Australian pass. Okay, so here's these type 2 regions that I was talking about, and this is pretty much the last thing that I will do before moving to just solving things out of the book. So all this is now is that we're taking a region and saying, now we know that y is bounded by C and D, and that x is the thing that we need to have functions to define the endpoints of. Right, it's the same thing, just wrote. It's basically Fubini's theorem as applied to these type 1, type 2 regions. So a type 2 region is a region D in R2, right, that is on the xy plane, given by the points xy such that y is in between C and D, and x is in between the 2 functions h1 of y and h2 of y. If f is continuous in the type 2 region D, then the double integral over D, and that shouldn't have an equal, you can see that I copied it, is equal to the double integral of C to D for y and h1x to h2 of x of f of x. Okay, so it's the same game, except that our regions are going to look a little bit different, right? And the integrals have been permuted with the order. Okay, so I've told you how to do type 1 and type 2 regions. What kind of region is this? I'll put on our thinking caps. Try to do some problem solving. You are correct and incorrect at the same time. Type 1 and type 2. Okay, well, minus 100 points from you. The next person I award points to are getting your points, which do equate to real marks. How about this? All right. So we can divide regions into subregions and then take integrals over them. So in this case, D1 is a type 1 region, right? We know the endpoints on x, and we can describe the endpoints on y. Right here, we know that y starts here and ends here, and x starts at this line and ends on that line. But in general, if you can take your arbitrary region and figure out some way of cutting it so that everything that is left are type 1 or type 2 regions, then we're gold. Right? Then integrating over sort of very sophisticated regions in R2 just becomes this process of dividing the region into manageable type of pieces, right? And you can see how a computer would be very useful just by trying to partition a region into manageable pieces. Okay, so here's the proposition that we need. If D is a region, and D, do you know what a partition is? If I give you a set, and that set has A, B in it, can you give me a partition of that set? Does anyone know the English definition of the word partition? To break into pieces is to partition something, not necessarily equal. So a partition of a collection of 2 objects, A, B, is the collection of objects of A and B. Because when you put them back together, you get the whole thing. So a partition in a mathematical sense is a set. You divide that set into, let's say, 2 pieces, but no piece can be in both things. It's a strict partition, except perhaps in these cases, to make things easier, we don't care if they intersect at the boundary. And that's not going to matter for us. So if you can take a region, D, and partition it into 2 pieces, then you can also partition the integral. And this is the statement that we needed to make that last picture useful. I want to say take the double integral here, and then add the double integral here. And this is exactly what this proposition is saying. So the upshot is that we can take integrals over regions that can be partitioned. Okay, so this is the final thing that we're going to do today. I'm not even going to do the integral. I don't actually give you an integral, but stuff like this is showing up on your, and maybe there's a couple comments I want to make on the web assign. But again, the difficulty, or one of the difficulties you'll have in the double integral questions, is it's simply determining the boundary, these regions. Are almost going to be more difficult than taking the integrals themselves. So if I said, here's a region, it's bounded by y equals x minus 1 and y squared equals 2x plus 6, right? So a line and a parabola. What are the type 1 and type 2 descriptions of D? Okay, what should we do? Picture. Always draw a picture, if you can. Right? Even on your tests. Yes? Well, we have to get away from this notion of vertical lines, right? Because functions are only functions, they only pass a vertical line test because we agreed everything that we write is y equals something. But this is very limiting, right? Because for a circle isn't a function. A circle fails the vertical line test, but we're going to use circles all the time, right? This is why we introduced graphs. Right? We care about the points that satisfy an equation. Because we could just take it and rotate it, which is pretty much what we're doing in these. But you have to be comfortable working in the whole plane now, not just things that passes for it, because it passes the horizontal line test if you'd like. It's a function in the other direction. I'll show you what I mean by this. So here are the two regions, and really the part of the region that is contained. Something I find hilarious is sometimes when I get pictures like this, and the enclosed region is tiny. Okay? The guy who wrote this book, we took a course with him, and the course was specifically in how to solve problems. And one of the pieces of advice that Dr. Stewart gave us, he said, your pictures should be enormous. Draw the biggest pictures that you possibly can, right? That's why I spend so much time drawing these pictures, even though they take me all day. Right? So here's the portion of those two curves that we're interested in, so don't continue drawing it and making this region smaller. But we care about this point, the leftmost point, minus 3, 0, right? Because we can see 2 times minus 3, it's minus 6, plus 6 is 0, right? So indeed, minus 3, 0 satisfies this equation. 5, 4, and minus 1, minus 2 satisfy both this and this. Right, let's check. 5, 4, does that satisfy this? Well, 2 times 5 is 10? Oh, that doesn't satisfy it, does it? Am I doing something wrong? Oh, yes. Okay, 2 times 5 is 10, plus 6 is 16, and 4 squared is 16. Great. Y equals x minus 1. So does 4 equal 5 minus 1? Sure does. What about this one? Minus 2 squared, that's 4, is equal to 6 minus 2. Yep. And minus 2 is equal to minus 1 minus 1. Perfect. Right? So these points satisfy both of those equations, and that's why they lie on the intersection. Right? That's why these graphs are useful. Okay, so what is the type 1 region? Give me the x interval on this. And what does our x range over on this picture? What is the minimum value for x? What is the maximum value for x? Minus 3 to 5. Perfect. And what is our minimum value for y and maximum value for y? Well, here, what if I'm here? I need to know where to start y and where to end y. Right? Minus 2 is where I should start, but only at x equals minus 1. Remember, the starting position and ending position on type 2 regions for the y is dependent on x. Only one of the intervals are going to be square, right, or going to be constant. So let's try again. If I'm here, where do I start and end? Well, what's this curve? It's labeled. What is this curve? Y squared equals 2x plus 6. Okay, so this is a trick question because this is not a type 1 region. I can divide it into 2 type 1 regions, but let's discuss this. So let's look at this point here. If I'm on the left-hand side of this point, if I'm here, say, then x starts at, let me me see, minus root 2x plus 6, right? Because this curve, okay, maybe I should go to the next one. This curve is two pieces, right? I can glue root x on top and minus root x on bottom. Right, so if I make this division, on the left-hand side of this division line, this D1 region, if x is between minus 3 and minus 1, here, then y has minimum value given by minus root 2x plus 6, and maximum value given by positive square root 2x plus 6. If I cross this threshold here, then the minimum value is no longer given by this curve, but by this curve. Right? So in D2, as x goes from minus 1 to 5, the minimum value for y is x minus 1, and the maximum value is positive root 2x plus 6. Right? So those are those two regions here. D1 is the points x, y such that x is between minus 3 and minus 1, and y is between minus root 2x plus 6, positive root 2x plus 6. And D2 are the collection of points from minus 1 through 5. That goes from x minus 1 to positive root 2x plus 6. So this is why I'm saying determining these regions, how to move, is probably going to be the most complicated part of your homework. But just be careful. If you write out, if you draw these graphs, right, and you can do so with a computer if you want, right? The Wolfram Alpha will happily plot two curves for you. Then it's just a matter of dividing them into these regions and being mindful about this, right? This is a good example because you have to break it into two pieces to make it, to do the two type 1 regions. Let's do type 2 regions now. So in a type 2 region, we know that the y's can be constant. So what range on the y do we have? What is our minimum value for y? What is our maximum value for y? 4. Okay, so we know that y goes from minus 2 to 4. So then if I pick any level between minus 1 and 4, what is the minimum value for x and maximum value for x? How about, let's start here. What's the minimum value at this cut? Yeah, 2. Yeah. So this one's actually kind of easier. Do this right. Oh, no, that's the last one. This is this one. So y is between minus 1 and 4. And we want to move from, oh, did I do this wrong? No, I did it, right? We don't have to separate this into minus plus, right? Because as soon as we fix the y, then it gives us an x. Right, so between minus 1 and 4, we go from x equals 1/2 y squared minus 6, right? That's what this line is in terms of x, to x equals y plus 1, right? So those are type 2 regions. So we have two options now for integrating over this function. We can integrate with the type 1 region, which would look like this for some function, or we can integrate using the type 2 region, which looks like this. So the moral here is, like as with Fubini's theorem, that reverting or reversing the order of the iterated integrals can be beneficial, right? So this is one of the tools in your tool belt now. If you're having difficulty with an integral, ask, is there a better way of representing my domain as type 1 and type 2 regions, right? It's shifting this notion that we're going to rotate and look at things differently to make things easier is basically the entire purpose of next week's lecture, right? The way that we're going to look at things will be in polar, in spherical, right? Specifically to make our computations easier. Okay, so those of you who want to leave can leave. Those of you who want to stay, we can spend 10, 15 minutes pulling questions out of here. Okay, so I printed off your WebAssign. I don't know what it's due, but this is the WebAssign. I did this almost in class. So there you go. It's pretty the same. This should be easy, right? Again, you're just integrating over this square region, so there's nothing that's involved here but remembering your single variable calculus. And just remember to treat one of the things as constant. Here's your first question where you have to first look at this region. Right, so this is a type 1 or 2 region. Yeah, if we know the specific region that x moves, that's type 1. Right, so that shouldn't be too hard, right? You want to integrate from, well, we can write this out. I think this is going to be, you want to integrate from 0 to 1 of this function, dx, and from 0 to x squared dy. Right? So, Yep. So that's how you're going to do that one. Roots x. Wait, no, x squared. What am I doing? That's better. Sorry, x squared. This one I did, in class, I just switched x and y. That's why I was getting confused. Because in your WebAssign, that's how the circle looks like. And so I did this. I just switched x and y. All right, so these two are really the ones that I wanted to talk about. What is the region bounded by the circle with center, the origin, and radius 3? We need to pull out a type 1 or type 2 region from this, and they've given us no equations. They've just given us a loose description. Sure, that's good information to have, but what's our ultimate goal? To determine these regions, right? And the first thing that we do with these regions is to take our equation and draw something. Well, why don't we just go ahead and draw? I don't need to know the equation for a circle to draw the circle of radius 3. Right, so, okay. Circle, can you see that, or? It's visible? Okay. Circle with center and radius 3. Okay, so here's how you do this. Here's a trick for all you math educators. Oh, here's a tip for you. If you ever want to draw a circle centered at something, never draw the axis first. Always draw the axis last. Right, so you do this, circle. That's not even that good, but I guarantee you it would have been worse if I. Yeah, you draw your circle. You always draw your circle first. So here's our circle. Here's the origin, 0, 0. Right, let's call this x. Let's call this y, and it has radius 3. And as you mentioned, we know that the equation for this is this. Okay, so I need to break this into either 2 type 1 regions or 2 type 2 regions. So you pick. You're going to say type 2? Okay, so type 2 means that which variable is fixed? Y. What is the min and max values for y? Perfect. Okay, so we know for sure that y goes from -3 to 3. Okay. So given we're at one of these levels of y, we need to know what the minimum value is and maximum value. How can we do that? So given that y equals a, we need to figure out what x is. Well, I can take this and I can isolate for x. Right? Although we have two things here. This region here on the left is going to be, yes, x equals minus root 9 minus y squared. On the right-hand side, we're going to have x equals positive root 9 minus y squared. So in fact, we have two regions, two type 2 regions, D1 and D2. The D1 are the collection of points such that y goes from minus 3 to 3, right? And x goes from minus root 9 minus y squared to what? Yeah, I think it may be 1. Like, I think I could say this is 9 minus y squared and it'll be fine. All right, so that's your region. In the end, your integral is going to look something like this. Well, you know that y goes from minus 3 to 3, so the constant thing should always be on the outside. And then on the inside, we're going to have minus 9 minus y squared to plus 9 minus y squared f. Where your f is going to be some randomization here. And the last thing maybe is, what about this? I don't actually know, but what's the sensible thing to do immediately? No. 1, 2, 1, 2, 3. Okay, so we have 0, 0, 1, or 0, 3, 1, 2. Type 1 means we know what the x is. Okay, so what's our x region? Oh, scheiße. Zero to equals 1, right? Okay, so we need to fix x maybe here. What do we move from to what? Right, that's what's tough about this question, right? You're just given some sort of region, and it's up to us to work it out. So the easiest way to describe a line is like this. So I like this. Y minus y naught is equal to m x minus x naught. So you just need any line, any point on the line and its slope. What's the slope of this guy? Well, we've moved over 1 and up 2. So rise is 2, run is 1. So this line is y minus 2 equals 2x minus 1. What about this guy? This guy's slope. Well, I move forward 1 and down 1. Try again. Line errors are tricky. Okay, so the other one is, okay, so this is this one. This one is, yeah, y minus 3 equals m, which is minus 1, x. Okay. So our region D should be what? All the points x, y, such that x is in this region. And y goes from this line. So 2x minus 1 plus 2. I probably should have simplified that, but whatever. Okay. So then I'm going to be doing a double integral from 0 to 1 from minus x plus 3 to 2x. Yes, thank you. Okay, that should be more than enough for you guys to solve your homework. At least my half. Okay, you can go home to your friends and lovers, and I'll see you guys next week. Friends and more lovers? Well, then you should become a mathematician, right? That's why I always tell people why I did math. Chicks and power.